The last section of the standard level part of the syllabus for astrophysics is cosmology, the cosmos. First we need to look at Olbers' paradox. First of all, we need to look at Newton's idea, Newton's model of the universe. The syllabus says that we should know that Newton assumed an infinite, in space and time, uniform and static universe. Infinite, uniform, static. Here's Newton. So this was called the perfect cosmological principle, which is homogeneity and isotropy. So first of all, he believed that the universe is infinite. It has no center. It was the same in all directions. It has no edge. In other words, if it had an edge, it wouldn't be uniform. And it's isotropic, which means in all directions it looks pretty much the same. This is his idea. Also, the universe is static. It has always been like it is now. Olbers' paradox. Newton believed that it was infinite, uniform, and static. The problem is, if the universe had been like this, the night sky would be infinitely bright, and we have to look at why the argument is that. He believed that it's uniform, which it isn't. He believed that it's static, which it isn't. And he believed that there's an infinite number of stars there, which there are not. If these three conditions are satisfied, then the universe would be infinitely bright, which it is not. And we have to use the inverse square law to be able to prove this. So Newton basically made a mistake. He made this assumption, and if you follow the argument in his assumption, the night sky should be bright, and it obviously is not. So this is a silly mistake on his part. So we need to look at Olbers' paradox. If the universe is eternal and infinite, and it has an infinite number of stars, then the night sky should be bright. And the idea behind this is that if you look in any directions, the very distant stars will contribute with very little light to an observer, but there are so many of them, they will contribute as much as the stars which are nearby, because there are many more of them. This is a qualitative description of it. And since there is an infinite number of stars, and each one is emitting a certain amount of light, then you're going to have an infinite amount of brightness from the night sky. Which it is not. So here's an idea: in any line of sight, there will always be a star with another star behind it if the universe is infinite and it goes on forever, and it always has been. One argument is that well, there might be dust between us and the final stars, and yes, then that would absorb some of the light. But if the universe is infinitely old, if it's always been the same and it's been like this forever, this dust would absorb the energy, and they themselves would be glowing because they would have heated up so much. Olbers' paradox. Now what we're going to do is we're going to have a slightly more rigorous mathematical approach to this. If we take the stars in a shell, a very thin layer of space at a distance of 1 unit from us, this is a very close star, and it's emitting lots of radiation towards us. If you go 10 times as far away, this area is going to have 10 times squared as many stars. But because they are 10 times far away, the radiation will drop off with the square of this distance. We have two factors. We have 100 times as many stars, but also the radiation from each one will be 100th of the intensity, because the radiation drops off with the square of the distance. So these factors will cancel each other out. If you go to 100 units, so the area is going to be 100 squared times as big, which is 100 times 100 is 10,000. You're going to get 10,000 times as many stars, but each star, because we're 100 times far away, is going to give us a 10,000th of the amount of light. So basically, each shell at each distance is going to contribute the same amount of brightness as far as we're concerned, as far as the light that we see. This contributes a lot from one star because it's close, but there's only one star. Here we have 100 times as many stars, but each star is providing 100th. So each shell provides the same amount of luminosity. So why is the night sky dark? Well, if Newton's idea is right, then it would be bright, but it's not, it's dark. So if the universe was an infinite number of stars, then it should be bright. This is a tighter mathematical treatment if we take a shell of radiation, a shell of space, the stars. We take all the stars from within this shell. The brightness from the stars will be the luminosity of that shell divided by 4 pi d squared, where d is the distance from us to this shell. The brightness from each star in the next shell will decrease by the same factor. So it's basically the number of stars increases with d squared, the radiation from each star reduces by d squared, so they cancel out. So each shell will contribute as much light as all the other shells. And how many shells are there in an infinite universe? An infinite number. So if we consider the universe finite and expanding, the radiation we receive will be small and finite for 2 reasons. If there's a finite number of stars, and they've had a finite lifetime, they have not been radiating forever. And because of the finite age of the universe, there are some stars that are so far away, they have not had time for their light to reach us yet. Also, another thing is the universe is expanding, so distant stars are so redshifted that the energy reduces, because remember E is equal to HF. As the frequency goes down, the energy goes down, so the radiation intensity will go down as well.